previous two sections, we talked about exponential and logistic functions, and we did some modeling with these. In 3.3 and 3.4, we're going to pretty much do the same thing, but we're going to do it with logarithmic functions. Okay, so we're going to talk about logarithmic functions, the basics about logarithms. We're also talking about their graphs tomorrow. Next week, we'll do some modeling with them. Now, inverses of exponential functions. In section 1.4, we learned that if a function passes a horizontal line test, then the inverse of the function is also a function. So we already know that if functions pass a vertical, or if equations pass a vertical line test, they're functions. If they pass a horizontal line test, they have an inverse that is also a function. We talked about that in previous sections. So an exponential function, b to the x, has an inverse that is also a function. This inverse is the logarithmic function with base b, denoted log of x to the base b. The b is always a little number there right next to log. That is, if f of x equals b to the x, with b greater than 0 and b not equal to 1, then f inverse of x is equal to the log of x to the base b. Now, here's what we have. These are graphs of an increasing exponential function and a decreasing exponential function. If we take an increasing function and we need to find the inverse of it graphically, we would reflect it over the line y equals x. That would be the inverse of this function. We already talked about log of x in section 1.3 when we worked on our chart and talked about analyzing those 12 basic functions. Now, an immediate useful consequence of this definition is the line between an exponential equation and its logarithmic counterpart. This is big, and you guys need to be able to do this. Y equals log of x to the base b if and only if b to the y equals x. So this is what we have. So really what we're doing, we're taking the base to the y power, and that's going to equal x every single time. It's a super easy thing to work on. You should have covered it last year in algebra trig, correct? So it shouldn't be anything new to you. Now, in example 1, we're evaluating the logarithmic expression without using a calculator. All right? We can do this a couple different ways. I'll show you one way here. In example 2, I'll show you a different way. What I would do here in example 1, let log of 8 to the base 2 equal y. What we can do then, switching this back to exponential form, 2 to the y is equal to 8. Now, can I make 8 into anything with a base of 2? 2 to the third power, right? So 2 to the y will equal 2 to the third. That means y will equal 3, correct? Yes, Lexi?
Oh, because 2 to the third is 8.
2 to the third is 8, yes. So the log of 8 to the base 2 is 3. Okay. Now if we do the same thing with b, this will equal y. So we'll have 3 to the y is equal to the square root of 3. Can I rewrite the square root of 3 as a number with a base of 3? Can I rewrite the square root of 3 as a number with a base 3? Yeah, Justin. 3 to the 1/2 power. That means then that y will equal 1/2. What about letter C? It's going to equal y, right? So that means then 5 to the y is equal to 1 over 25. Yes? Can I rewrite 1 over 25 as something with 5s in it? I can't write 25 as something with 5s in it? What can I do? 5 squared, right? Now, usually we always say we want positive exponents, right? But in this case, I need 5 on the top. So how can I move this 5 squared to the top? What am I going to do with the exponent?
Make it negative.
I'm going to make it negative. So 5 to the y equal 5 to the negative second power. That means y will equal negative 2. All right. Questions so far on A, B, and C? All right. Let's do D and E. Should be nice and easy for you. Again, we're going to let it equal y. That means 4 to the y will equal 1. 4 to what power will be 1? 4 to the 0 power. We've talked about this already. So really what we can say, we can go like this. 4 to the y is equal to 4 to the 0 power, which means y will equal 0. Do you need that blue step? No, you don't need the blue step, but it might be helpful if you need to. A little bit of explanation. Now in E, again, we're going to have 7 to the y is equal to 7. What power is really on the 7? You don't see it, it's a 1. That means y equal 1. Now, we can generalize these relationships. Observe example 1. Log of 1 to the base b is 0 because b to the 0 is 1. Log of b to the base b is 1 because b to the first is equal to b. Log of b to the y to the base b is equal to y because b to the y is equal to b to the y. And then the last one here, b to the power of log of x to the base b is equal to x because it ends up being log of x to the base b is equal to log of x to the base b. Now let's talk about that last one there because that is kind of different. Let me move these a little bit. What we're given, we know log of x to the base b is equal to y, which means b to the y is equal to x, right? That's what we know so far. In this case, though, we're given b log of x to the base b, and that's equal to x, right? If I had to switch this back this way, we'd end up getting log of x to the base b is equal to log of x to the base b. That's why this works. So it's just saying these are equal. So switching back from exponential to logarithmic form, these are equal. Okay, we'll see that again and again, especially with, if you look at example 2c, we'll see it. Okay? Now in example 2, I want you to use the chart that we just created. Not just created, but we just saw in red. All right? Can I rewrite 8 as something? 2 to the third power. We know the answer is going to be 3. But I just want to do it like this. Now if we look at the chart, we're using this right here. Correct? So it's going to be the power. Our answer will be 3 using that property of exponents there. Okay? We can do the same thing with b. We're using that same property for your answer to be 1/2. Same exact property. Once you do a lot of these, you'll understand that we're doing the same thing over and over again. Yeah?
So if you enter that into the calculator, the answer would be 1/2.
Well, we haven't really talked about how to enter this in our calculator, but the way you would enter this into your calculator, because our calculator doesn't work with bases as much, we'd have to use a change of base formula. We take log of the square root of 3 divided by the log of 3. And you get 0.5. Okay, it's a change of base formula, which we'll learn in a later section. Okay? Even here, log of 8 divided by log of 2 will be 3. Okay, simple enough. Now, if this one's going to be a little bit different here, so we're going to actually change it back into log form. My answer is going to be 11 from the chart, but if we had to change this back into log form, we'd have log of x to the base 6 is equal to log of 11 to the base 6. Because the x and the 11 are in the same spot, that's why my answer is 11. Logs. Base 10. The logarithms of base 10 are called common logarithms. Because of their connection to our base 10 number system, the metric system, and scientific notation, common logs are especially useful. We often drop the subscript of 10 for the base when using common logs. You think about it like this. Every time we have x to the first power, do we ever write 1 for x to the first power? No. Every time we write the square root symbol, do we ever put a 2 over that square root symbol so we know it's the square root? No, it's just understood. Same thing here. If you don't see the base, it's understood to be 10. Now, the common logarithmic function log of x to the base 10 is simply log of x. It is the inverse of the exponential function 10 to the x. They are inverse of each other. So, log of x, y equals log of x, if and only if 10 to the y equals x. Actually, I should say x here. All right? There's that. Applying this relationship, we can obtain other relationships for logarithms with base 10. So it's kind of going back to that same chart we just used. Log of 1 is 0 because 10 to the 0 is 1. Log of 10 is 1 because 10 to the first is 10. Log of 10 to the y is y. 10 to the log of x is equal to x. That's what we have there. Now, let's evaluate here. Shouldn't take us too long to do this. All right? We can do it with the charts, or you can do it using equals y. I'm going to choose to do it equals y right now, so 10 to the y is equal to 100. Can I write 100 as something with base 10? 10 to the second power. So 10 to the y is equal to 10 to the second power, which means y is equal to 2. If we do the same thing for b, I'm going to use the chart this time. This will equal log of 10 to the 1/5 power, which will simply equal 1/5. Now you can see that right here. Log of 10 to the power of y will equal y, so the power is going to be what it equals. Okay? I'd like you all to try C, D, and E. All right, with log of 1 over 1,000, we can really rewrite this as log of 1 over 10 to the third, which could be rewritten as log of 10 to the negative third, which means this will equal -3. All right, now you can also do it like we did in question A, or in problem A here, where it equals y. That means 10 to the y will equal 1 over 10 to the third. 10 to the y will equal 10 to the negative third, which y will equal -3 also. Okay, now what we'll have here is this 10 log of 6 will equal x. If we wanted to change this, we have log of x to the base 10 will equal log of 6 to the base 10, which means x will equal 6. Now, you could also use this property right here. 10 log of x will equal x, because log of x will equal log of x. And that's pretty much what we have here. Now, using that same property as in A, B, and C, we could see that log of 10 to the third power will equal 3. Are there any questions on example 3 at this time? Sure. Would you like to use it using the properties or using let it equal what? Okay. Well, they're both pretty much the same, so let's do this. So if we look at C, and we set it equal to y, right? That means 10 to the y power will equal 1 over 1,000. Well, 1,000 we can, when the base, if we remember, if we don't see the base, it equals 10, right? Now, we can really write 1,000 as 10 to the third power, right? Which means then, what's that? Yes, because it has 3 zeros. This will win. Okay? Your answer will be -3. Does that make sense?
So whatever, like, the exponent is, that's what your answer is?
Yes. Now, common logs can be evaluated by using the key on a calculator, as illustrated in example 4. Now, use a calculator to evaluate the logarithmic expression if it is defined, and check your result by evaluating the corresponding exponential expression. Okay? So I want you guys to find log of 34.5. Your log button actually says log on it. Log of 34.5. 1.54. Actually go 3 decimal places. 1.538. So there's your answer. Now, to check to make sure your answer is right, remember the inverse of log of x is 10 to that, or 10 to a power. So we'll take the inverse of our answer, so 10 to this power, and you'll see that you do get 34.5. So that tells you it is correct. Okay, do you have a question? Second log, if you press second log, you get 10 to a certain power. And then second negative sign here is your answer. That just shows you that you are correct. Yes, Lars?
I do mine, just picking off 1.54 and go.
Did you press your mode button? Okay. Make sure float is highlighted.
Just for your floating.
Okay.
Cool?
Yeah,
Now, find log of 0.43. You get negative 0.367. Now, second log gives us 10 to, I want to go to this power, so second negative, we'll get 0.43. Now, what about log of -3? What do you guys think? Log of -3 doesn't work, right? Why is that? So this does not exist. Why doesn't log of -3 exist? If we simplify this, if it equals y, is there any power of 10 that I could put in that will give me a negative number? No. If I put negative powers in, I'd get 1 over 10, or 1 over 100, something like that. So I'm never going to get a negative. The domain of log of x, is 0 to infinity. So that's the domain. So you cannot have a negative x value in log of x there. Okay?
Have 0 though?
You can have 0. No, actually you cannot have 0 because it won't exist there. Right? Because with the parentheses there instead of a bracket, it doesn't exist. Okay? Yes. Okay, sometimes with the newer calculators, if you go press your right button, because you have an arrow, right? Keep pressing right until you get to the end. What do you notice? And it log of -3. Okay. Second log of -3. Well, that'll work. Okay. Log of 0.43. Forget this. The second log. Good. Now, are there any other questions on example 4? Any questions at all? All right. Now, changing from logarithmic form to exponential form is sometimes enough to solve an equation involving logarithmic functions. So, solve the equation by changing it to exponential form. What's the base here on A? Base is 10. So, 10 to the third will equal x. Switch it to exponential form. What is 10 to the third power? 1,000. Now to check this in your calculator, what we do, we'd go log of 1,000 to check it into your calculator, and we do get 3. Okay? Now for B, what is your base in B? Base is 2. So we're going to have 2 to the 5th is equal to x. That means x will be 32. Now, there is a way to check this, which we'll talk about in the next, I believe it's tomorrow or the next section. If I do log of 32 divided by log of 2, I will get 5. Okay, it's called a change of base formula, which we'll learn a little bit later. But that's really what that's how you check that one. How about C? So 10 to the 4th will equal x. That means 10,000 will equal x. Again, if we wanted to check it, log of 10,000 will be 4.